Hello, my name is Corbin Gustafson, and this is my submission for part one of the Aerodynamics final project. So the first thing that we're going to do is go ahead and look at the geometry. So the geometry was made with the 150 to 1 length to height ratio. So the length is 15 meters and the height is 0.1 meters right here. It's just a simple rectangle with the bottom left focused on the origin. All right, here we are in the meshing software. So as you can see, I did a quadrilateral dominant meshing. So lots of small squares, and my element size was 0.005 meters. I also named each individual side, top plate, bottom plate, pressure outlet, and velocity inlet. And you're going to need to name the top and bottom differently so you can add a velocity to the top plate. All right. All right, so now we have the solver open, so I'm going to just quickly go through everything that I did. I have the viscous laminar model on. For materials, I created a material called engine oil. The engine oil had a density of 850 kilograms per meters cubed and a dynamic viscosity of 0.25 Pascal seconds. For the boundary conditions, the incoming free stream velocity is 5 meters per second. The top wall is moving to the right at a speed of 3 meters per second. Still no slip condition on, but moving to the right. The bottom plate is stationary. So it's a stationary wall, still no slip on. Now I'm just going to go ahead and initialize this. All right, the initialization is finished, and now I'm just going to go ahead and run the calculation here. All right, so it completed, and the solution converged in 83 solutions. So that's good. Now let's get on to part A. So part A was calculate or show the velocity contour. So here's the velocity magnitude contour, and here it is zoomed in. The version I have on the report had this as a solid lines, but this one has the grid on. I think because it's, yeah, there you go. So as you can see the boundary layer growing over time. The next part B had to do with the pressure contours. So we're just going to go ahead and set it on static pressure. This is to be expected because as this goes across, velocity is increasing, so dynamic pressure is increasing, which means the static pressure must also go down. So now if we go to dynamic pressure, we would expect to see exactly the opposite. And we do. We can see that the velocity in the center is increasing. Now we're going to go ahead and go to total pressure. And here we go. See. All right, now for part C, we're going to have to make, I made two lines for part C. I made an inline and a midline, and those are vertical lines, and that's going to allow you to take the velocity over that line and plot them on an XY plot together. So that's midline, inline. Let's go ahead and save that plot. And so here you can see the velocity over that vertical line for both the inline and the midline. And the velocity, the peak velocity for the inline is just slightly higher than the one for the midline. And that makes sense because the velocity profile continues to develop. even just ever so slightly, it's developing. Now for the next part, when you're looking at this line right here, you want to know what is the maximum velocity and also at what height does that occur. So if we go over to this MATLAB code, I got those XY coordinates from that plot, and I separated them into the inline and midline. I found the maximum velocity in this specific column, which column 1 was the velocities. And then I found the index of the velocity of that maximum velocity, and then I found the height that velocity occurred, or that index was at, which was just the second column of the midline matrix. So if I run this, let me scroll to the top. You can see that the location of the maximum velocity is 0.0511 meters. And that makes sense because you would expect that, well, normally like the location of the maximum velocity would just be the height of your volume divided by 2. But since we have a plate that's moving to the right on the top, that place where maximum velocity occurs at is going to be shifted slightly higher. So where if both walls were stationary, you would expect that to be 0.05 meters. Here it's 0.055 meters. So that makes sense. And we see that the velocity is 6.8 and a little bit meters per second. And if we go back here, yep, that checks out. Now for the next part, we're back to MATLAB again. So I needed to find the pressure, the average pressure at the beginning and end, and to find the dP dx, the pressure gradient. I was just thinking, okay, I'll take the pressure at the end and at the beginning and divide that by the change in length. So change in pressure divided by change in length. To get these values right here, what you're going to want to do is you're going to go back to ANSYS, go into report definitions, create a new area weighted average report, and I want to find static pressure difference between the end line and the start line. So we'll go ahead and compute that. So this value right here is probably our inline. So yep, end. And this value here is our start line. So start line. And so I just took the difference of those, divided it by the change in length, and that gave me negative 681.78 dP dx. Now you also need to compare that to theoretical results. And so for the theoretical results, I used this equation here. This is just when you have this type of flow with one moving wall, you can use this equation, solve it for dP dx or dP dl in my case. And so the top was moving at 3 meters per second, incoming free stream velocity was 5 meters per second. The height was 0.1, and the dynamic viscosity was 0.25. Also in this equation, you need the middle, I guess you could call it. And for that, for us, I'm going to use the max V height inline. So that's that value. That's a 0.0551. And when I plugged all that into this equation, I got the outcome of negative 676.4, which is very close to the ANSYS results. So the theoretical model and the ANSYS model match up pretty well. All right, and that's all for Aero Final Project Part A, or Part 1. Thank you so much.